So I'm going to be talking about learning Bayesian networks. What that means is Bayesian networks are structures that model probability-based relationships in the real world, and we can use machine learning to discover their structure through observing data. So I'm going to start from the most simple Bayesian network, which is a single node, and go up in complexity and explain techniques in order to learn these. So the single node Bayesian network is just a probability distribution over all possible values of the node. So I'm going to be using an example from AIMA chapter 20, which is a bag of candies. And we don't know the proportion of different flavors of candies in the bag. So we want to figure out what the probability is that we're going to pick a cherry candy or a lime candy from the bag. And we have these hypotheses over here. What these say is how much of the bag is cherry versus how much is lime. So the first hypothesis is that 100% of the bag is cherry, which would mean a 100% probability of picking a cherry candy. The second hypothesis is 75% cherry and 25% lime, which also corresponds to the probabilities that you would have of picking those candies. So we want to learn the probability distribution that is the actual distribution based on looking at data. And what's interesting about this is that we're sort of looking at probabilities of these probabilities. So this prior on the hypotheses is going to say how likely it is we believe that each of these hypotheses is the actual distribution. So how can we learn the actual distribution? These are some useful equations. First, the probability of the data given a hypothesis. This is basically a sequence of data observations, so that would be picking multiple candies out of the bag and recording whether they were lime or cherry. And we're going to get the probability of seeing a data sequence given a hypothesis by just finding the product of each of those data points given the hypothesis, and we'll see an example later. But then the probability of a hypothesis given the data, we can simply use Bayes' rule and multiply the probability of the data given the hypothesis, which we just calculated here, by the prior belief on that hypothesis. Then, and if we also want to predict the next candy drawn based on the candies drawn so far, we can predict this quantity x based on the data by just summing up over all the hypotheses. So let's do an example of trying to predict or learn this node's distribution. So imagine that we have these data points drawing lime and then cherry and then cherry. So the probability of this data set given the hypothesis 1, which was that the bag was 100% cherry, is going to be first calculating the probability of that data based on H1. So the probability of drawing a lime candy from a bag that has all cherry candies is 0. Then the probability of drawing cherry candy from that bag is 1. And 1 again for the second cherry. Then 0.1 is multiplying by the prior belief that it was all cherry, which was 0.1, so that gives 0. Doing that again for hypothesis 2, that hypothesis was that the bag was 0.25 or 25% lime and 75% cherry, which results in this sequence multiplied by 0.2 for the prior belief. We can then calculate all of those for the remaining hypotheses and then normalize this. And we can see the results here. The most likely distribution of this node is hypothesis 3, which was half and half. This is both because the data aligns with that pretty well and because the prior was the highest for that hypothesis. Then H2 and H4 actually had the same prior, but H2 comes out ahead because we observed more cherry data points. So as more and more data points come in, the priors can be updated for each of these hypotheses, and the new data can be used to weight them until it converges to the most accurate hypothesis. And we're going to see a code example of this. So in this Jupyter notebook, I'm going to demonstrate learning a distribution over a single node, which is the most basic form of learning a Bayesian network. So here I've defined the different hypotheses. with the probability of cherry coming first and then the probability of lime coming second. So this pick candy function is just going to pick out a candy based on the cherry probability. So this normalize function is going to normalize the distribution. Then this learn function is going to basically repeatedly pick a candy using this picker function that'll be initialized with probability, then update the priors based on that, normalize the new priors, and then repeat that for the number of trials that we specified. Finally, this function is just going to plot the beliefs in all of the hypotheses as the learning progresses. So then we're going to do this for all of these possible hypotheses. So what that's doing is for each hypothesis, we're going to make it actually be that hypothesis and then watch the algorithm learn that it is that hypothesis. So when we graph these, we see that here the actual distribution of candies was 100% cherry and 0% lime. And the algorithm pretty quickly learned that that was the correct distribution. You can see down here at the purple line, the first cherry candy that it picked, it knew that it could not be the all lime, so it went down straight away. This orange line here, 0.75, 0.25, so originally it thought that it might be the 0.75, 0.25 lime bag, but then as more and more cherry candies got picked, it eventually realized it's probably not that bag. And then similarly, we have graphs for each of the other hypotheses, and we see that it learns pretty well the correct hypothesis each time. Some of them it's a little less sure. Like this one, it went back and forth a lot, and we can see that as these two lines are symmetrical, which is interesting because basically when it picks, when it's sort of trying to decide between two possible hypotheses, when it picks a cherry one, it'll go up for the one with more cherry and down for the one with more lime relative to each other, and then the other way around. But eventually it does figure out that the actual distribution is 25% cherry and 75% lime. So moving on to the second most complicated Bayesian network with a causal relationship. So this one is going to have two nodes, one for flavor and one for wrapper color. And we know that flavor influences wrapper color in some way, but we're not sure exactly how. So we can define this Bayesian network using parameters, and the parameters are going to help us define these conditional probability tables that define a Bayesian network. And we're actually going to be able to figure out all 6 probabilities with only 3 parameters. So A is going to be the probability that the flavor is cherry. B is going to be the probability that the wrapper is red given that the flavor is cherry, and so on. And then if we want the probability that the wrapper is green given that the flavor is cherry, we can just subtract B from 1. So you can see that all of these probabilities can come from A, B, and C. So then our task is going to be figuring out the values of A, B, and C. And to do that, we can use this approach called maximum likelihood parameter learning. And what this is going to do is learn the parameters based on data that we've observed. So to name this data, C is going to be the number of cherry candies that we've observed so far. L is the number of lime candies that we've observed so far. RL is the number of lime candies with red wrappers that we've observed so far, and so on. And then we're going to want to maximize the likelihood of seeing the data that we did by tuning the parameters. So basically, we want the parameters of the Bayesian network to make it so that the Bayesian network most accurately describes the data that we've seen. And we can do this more than once to do learning. So to do this, first write an equation for the probability of the data based on certain parameters. So this is going to work just by multiplying together all of the observations. So basically, theta is the probability that the flavor is cherry, C is the number of cherry candies unwrapped. So this term is basically figuring out how likely it is that that number of cherry candies was actually unwrapped. And similarly for these other 5 terms. Then we take the logarithm of that equation, and what that's going to do is divide it into 3 easy to look at terms that each have one of the parameters and no other parameters. Why would we want that to happen? Because it makes it easy to take partial derivatives based on all the parameters. So, for example, when we take the partial derivative with respect to theta, this parameter is the only one we're going to have to consider because theta is not in either of these other ones. And so these will go to 0. So when we've found all 3 partial derivatives for all 3 parameters, we end up with these equations. And how we're going to use these equations is we can see that each parameter gets its own formula based on events that we've already observed. So what this means is these parameters can actually be learned directly from the observed data. And these formulas are pretty intuitive. For example, the one for theta sub 1, which is the probability that the wrapper is red given that the flavor is cherry, is calculated given the number of red cherry candies observed over the total number of cherry candies observed, which is pretty close to how we would want to approach finding this probability without all of this Bayesian stuff. So it's pretty intuitive. And this method can be used on more and more complex networks. We just have to formulate it as a parameter problem where all the conditional probability tables are put in terms of parameters, and then use this method to learn the parameters. So this works really well when we already know the structure of the network. We can figure out what parameters we need to learn. But if we don't know the structure of the network yet, there's also ways to learn that. So this brings us to the third most complicated Bayesian network, where we're going to be learning causal relationships between the nodes. And this example is coming from a video by Richard Neapolitan called Learning Bayesian Networks. I believe he's also the author of a book called Learning Bayesian Networks. So we're given these 4 nodes, W, X, Y, and Z, and we can collect data on them. So each data point is going to contain a value for W, X, Y, and Z. And we want to know how we can learn the relationships between them, or the structure of the Bayesian network. So how we're going to do this is to search over all of the possible structures. So we're going to just begin with nodes and then create different structures, and for each structure evaluate how well it fits the data. So how are we going to evaluate the fit of the data? So we can either tell how well the network models the data. So this is going to be like, given the network, does it actually say the data is going to look the way it does? Or we can figure out whether the network implies the conditional independencies found in the data. And this is what we're going to use in our example because it's easier to demonstrate with data. So how we're actually going to find conditional independencies from data, there are statistical tests of independence such as t-tests that can tell to a reasonable degree of certainty whether 2 variables are independent given data, or whether they're independent given a third variable. So a simple example is in the table up here. 2 variables, x and y. They appear to be independent. This is because the proportion of y being 1 versus 2 doesn't change when the value of x changes. And the proportion of x being 1 or 2 also doesn't change when y changes. So it appears that these 2 are independent. This isn't for sure, and we need more data, and our belief might change as we get more data, but for now it's a good start. So let's say that from the data we get that, and then we also get that W is independent of X and Y given Z. So with these conditional independencies, how can we figure out what a good structure would be? Well, there's this theorem that says that there is an edge between 2 nodes in a network if and only if there are no conditional independencies between them. So from that, we can figure out X, Y, and W all have conditional independencies between them, so they're not going to have edges. But Z does not have conditional independencies with any of them. So we're going to draw edges between Z and all of the other nodes. Next step is figuring out which direction these arrows actually point. And we can do this because we know that for groups of 3 nodes, there are certain structures that imply independence or conditional independence. So since we know that x and y are independent, we know that this V structure is the only way that that can be satisfied given these connections. Then the only remaining line to figure out is this one between z and w. And we can use a similar approach here. We could look at either y, z, and w, or we could look at x, z, and w. So let's just look at x, z, and w. We know that w and x are conditionally independent given z. And there's multiple ways that we could draw the arrows to satisfy this, but we've already drawn the x to z arrow. And we know that if w points to z, that implies that x is independent of w, but it does not imply the conditional independency that we want. So we know the arrow has to go in this direction, from z to w. So this can be sort of a goal test that algorithms can use to check whether structures that they're coming up with are valid while learning. And this helps them create structures and reevaluate and rebuild the structures as new data comes in. Now I want to talk a bit about how we'd approach networks with hidden variables. So this is the most complex so far because it involves not only learning parameters of the nodes for the conditional probability tables and the structure of the relationships between the nodes, but it also involves variables that we don't even know for sure are there. So how can we learn structures with variables that have no way to observe them? So the first approach is to tell the algorithm some hidden variables that you know are there. That approach would be good if you already know what hidden variables are likely to describe the data. For example, if you're studying heart disease, you know that heart disease is probably going to be a variable. Approach 2 is that you don't tell it what the hidden variables are. Then, 2 different types of algorithms. One just doesn't use any hidden variables and just creates a structure based on the observed parameters. That would probably come up with a pretty complex model with lots of relationships between the nodes, but it could still describe the data pretty well. Then the second way is to create hidden variables itself and then test the fit with those hidden variables. And that would work similarly to the last example, except that it can also create and delete hidden variables as it's searching. So it just sort of adds an additional thing that the search algorithm can do when it's coming up with possible states for the network. Expectation maximization learning is one algorithm to learn hidden variables, and it's a pretty general algorithm, but basically the approach is to first compute the expected values of the hidden variables, then pick the parameters or structures that maximize the likelihood of the data you've observed given those hidden variables. And then it sort of iterates and updates the parameters as it figures out what those hidden variables might be. So you can see in this equation, it's basically theta is the set of parameters, so it's updating that to maximize the summation. And the summation is the expected log likelihood of the data so far based on what we think the hidden variables are so far. So this should eventually converge to something that fits the data pretty well. Another thing to be careful of when finding and creating structures for data is that they might get too complex. And this is because adding more relationships is probably not going to decrease the likelihood of the data. So we want to avoid adding too many relationships or nodes to the network. So there's a trade-off between complexity and the degree of fit. So most of these algorithms end up adding a penalty for complexity so that the networks end up still having a reasonable number of relationships. So we've gone over several ways to learn Bayesian networks. So hopefully this demonstrates how we can learn the structure of a probabilistic domain by looking at data and using machine learning. And this is just one form of machine learning which takes data and uses it to model results. So we can actually then use the Bayesian networks that we create from these methods and then use them to predict new values of data.